For the results this week, it'll be very convenient for us to be able to integrate over the set of m-dimensional planes in Rn. So to do this, we need to introduce the notion of the Grasmannian and Grasmannian measure. So the nm Grasmannian is defined to be the set of all m-dimensional subspaces of Rn. You can show that this is a differentiable manifold, but we won't rely on this fact in this class. We can define a metric on the Grasmannian by defining the distance between two m-dimensional planes, which will just abuse notation and write as if they were vectors. We define this distance to be equal to the norm of the operator that is the difference of the two orthogonal projections onto v and w respectively. So you can rewrite the definition of this norm as follows. So geometrically, what you should really be thinking about this distance is that this ends up being equivalent to the angle between two planes v and w. So in fact, if we're looking at the Grasmannian of lines, then it turns out that this distance between v and w is comparable to the angle theta between these two lines. Now, observe that the orthogonal group acts isometrically on the Grasmannian in the sense that it preserves distances exactly. Distance between v and w under an orthogonal map is unchanged. So recall that we're denoting by O of n the orthogonal group, which is a set of orthogonal transformations on Rn. Now, notice that this is a topological space, since we can realize this as a manifold lying in some high-dimensional Euclidean space. In particular, it's a compact manifold. Moreover, there's also a natural group structure, of course, through composition. And so by Haar's theorem, there exists a Haar measure defined on the orthogonal group. So this is a measure that such that the measure of sets are preserved on the group actions. So as I say, if I have a set A, then if I take G times A for some element of my group G, then the measure is unchanged. And the same thing if I take A times G from the right. So using Haar measure on the orthogonal group, I can define a measure on the Grasmannian. So first of all, I fix a plane V0 in G and M, and I define my Grasmannian measure to be the measure, the Haar measure, of the set of orthogonal transformations so that the image of V0 under my orthogonal transformation is inside the set A. So you might think that this seems like a peculiar definition for a measure on the Grasmannian. However, it has some very useful properties. So first of all, notice that this measure is independent of our choice V0, which isn't too bad to show. Secondly, because the original Haar measure was invariant under orthogonal transformations, so is the Grasmannian measure. So if I have a set of planes and then I look at the image of these planes under a under an orthogonal transformation, then the Grasmannian measure of these sets is unchanged. Moreover, there is a relationship between the m-dimensional Grasmannian measure and n minus m-dimensional Grasmannian measure. So that is to say, if I have a subset A of m-dimensional planes, and I look at the set of orthogonal complements, which is going to be a subset now of the G n minus m Grasmannian, then the Grasmannian measure of A is the same as the Grasmannian measure of A perp. So there's a natural way of identifying the Grasmannian measure on the set of lines and hyperplanes to surface measure on the sphere. So we're going to let sigma to the n minus 1 denote normalized surface measure on the sphere. So in this way, the measure of the unit sphere is just equal to 1. Then we can identify the Grasmannian measure on the set of lines with surface measure as follows. So given a set A of lines, we take the union of all the lines in this set intersected with the unit sphere and then take its surface measure. And this turns out to be equal to gamma n1 of A. Similarly, if we look at a set of hyperplanes A, then the Grasmannian measure of the set of hyperplanes is the same thing as taking the union over all orthogonal spaces to these hyperplanes, which will be a union of lines once again, and we look at their intersection with the unit sphere and again take surface measure of this set. So why is this true? So The proof involves showing that each pair of measures that we've defined, so for example, the Grasmannian measure on Gn1 and this new measure that we've defined, what you do is you show that each one of these measures are uniformly distributed on their respective domains. So recall that a measure, mu, on a metric space is said to be uniformly distributed if the measure of any balls of a fixed radius are equal to each other and are positive and finite for all radii. So there's a theorem that says that if you have two measures, mu and nu, that are uniformly distributed Borel measures on a separable metric space, then in fact they are a constant multiple of each other. So thus, because both these measures, gamma and 1 and surface measure on the sphere, are both normalized, once you show that they are uniformly distributed on the Grasmannian, then this theorem implies that they must equal each other. The Grasmannian measure satisfies some useful estimates, so I might record these inequalities so you can have them on hand for when we study Hausdorff dimension of orthogonal projections of sets later on, since we'll use these inequalities explicitly in our estimates. There's one other object that'll be very important for us when we study the Falconer sundial, and it's the Grasmannian bundle. So it's defined as follows. The Grasmannian bundle, denoted U and M, is defined to be the set of all pairs v, x, where x is an element of v and v is an element of the Grasmannian. So the topology on this space we define to be such that a sequence of pairs vn, xn converges to a pair vx if and only if vn converges to v in the topology on the Grasmannian, and also if xn converges to x in the Euclidean topology. So there's a natural measure that we can define on the Grasmannian bundle, defined as follows. So first, we define this measure for open sets. So for an open set, we define the MNM measure of A to be the integral of the Lebesgue measures of the set of x in V such that the pair V of x is in the set A, and we integrate this quantity over all planes in the Grasmannian. So we defined it first for open sets, but then you can show that this extends to a Radon measure defined on the whole Grasmannian bundle.